In this video, we will be focusing on the a value. The a value is a number that is attached to the function by multiplication and it is seen in front of it. And the a value is something that you have seen in grade 10 when you were looking at parabolas. And in grade 10, you saw that the a value represented a vertical stretch or compression or a reflection over the x-axis. So when the absolute value of a, meaning the absolute, these straight lines around the a, that just means whatever that number is, you turn it positive. So the absolute value of -5 is +5. So if we look at the absolute value, if it's greater than 1, then we have a vertical stretch. And we would communicate that by saying a vertical stretch by a factor of whatever a is. If the absolute value of a is less than 1, then we have a vertical compression. So that means your function is being squished down towards the x-axis. Now all of these vertical transformations, they're affecting your y-coordinate. So when a function is being stretched, the y values are being extended. Or when a function is being vertically compressed, the y values are being squished down lower towards the x-axis. And the reason you have to mention that it's a vertical stretch or compression is because there are also horizontal stretches and compressions, so you have to differentiate between the two. But the a value is all about the vertical. Next, if your a value is greater than 0, meaning it is positive, there's nothing happening besides potentially a stretch or compression. But if the a value is less than 0, so if it is negative, you have a reflection over the x-axis. And again, it's important that you specify which axis because you can also have reflections over the y-axis. All right, so now that we know what the a value represents and we've refreshed on that, let's try to apply that transformation to one of our base functions that we've looked at. So first we have f at x equals 4 to the x. That is an exponential function. And we are trying to apply 5 f at x. Notice the 5 is attached to your function by multiplication. That's what makes it a vertical stretch, compression, or reflection. So first I'm going to write the equation and I'm going to label my transformed function as g of x. And all I'm going to do is take the 5 and put it right in front of the base function. So I have 5 times 4 to the x. And this 5 represents a vertical stretch because it is greater than 1 by a factor of 5. And that's it. There's no reflection because the 5 is not negative. Okay, let's try the next one. For the next one, we have our rational base function, so 1 over x, and we are applying -1/3 f at x. So I'm going to start with my transformed function, and once again, that a value is just going to get written right in front, and then I'm going to open a bracket and write the base function. Now, because we have a negative and a value other than 1, we do have 2 transformations here. So the negative tells us that we have a reflection over the x-axis. And then ignoring the negative, because we've already dealt with it, the 1/3 represents a vertical compression by a factor of 1/3. So we do have 2 transformations here. And also take note that I said by a factor of 1/3, not -1/3. The negative told me the reflection, the 1/3 told me the compression. All right, I want you to pause the video here and I want you to try the parabola on your own. So you have x squared. I want you to write the equation for 2/3 f at x and then state the transformation and then come back to the video. So for your transformed equation, hopefully you have 2/3 x squared. that 2 over 3, it's positive, so there's no reflection, and 2/3 is less than 1, so you should have a vertical compression by a factor of 2/3. Okay, the last one, we have the cosine function. I want you again, pause the video, write the equation, write your transformation or transformations, and then come back. All right, so for your function, hopefully you have negative 5 over 2 cos x, and you can use any letter. I used g of x, but you can do anything other than f of x. And then you have two transformations here. You have the reflection over the x-axis because of the negative, and I hope you stated that it was a vertical stretch by a factor of 5 over 2, because 5 over 2 is actually 2.5, which is greater than 1. So just because you see a fraction, it doesn't mean it's a compression, so be careful with that. All right, let's try some actual graphing now. So we're going to graph the base function for each example. We're going to write the transform function. We'll state the transformations to guide us. We'll graph the transformations, then state the domain and range. Now with the a value, you notice that sometimes you have two transformations, a reflection and a stretch or compression. When that happens, you can either graph it all at once, or you can apply those two transformations in two different steps. I personally like to do it all at once, but I will show you in the first example doing it in 2 steps, and then after that I'll do it in 1 step, and the choice is yours. Do whatever works best for you. So let's start off with just graphing our sine x function. And because it is sine, we know we're starting at the origin, and every 90 degrees we're going to go to the key point. So with sine, we head upwards towards the maximum. And make sure after you connect, you put arrows at the end and you label this as f at x, because we are going to have multiple functions on this grid. So you want to make sure you label them so that the reader or the marker, me, knows what you're doing and what you're talking about. So now that we have that, let's go ahead and write our transformed function. Again, I'm going to label it as g of x. And because we have that -4 in front, I'm just going to put -4 in front of sine x. So this tells me 2 things. I have a reflection over the x-axis, and I also have a vertical stretch. I'm just going to write vs for vertical stretch by a factor of +4. Okay, so I'm going to apply these one at a time. So I'll start with my reflection. You could have started with your stretch first, it doesn't matter. So with the reflection, because it's over the x-axis, any point that isn't on the x-axis will just go on the other side. So these points here that are at 0 on your midline, they're not going anywhere. They can't be reflected if they're on the x-axis. But the maximum will now go to the minimum, and the minimum will now go up to the maximum. So I'm going to do that. I'm going to reflect those 2 points. And now I'm going to connect my dots. Now when I label this new function, all that I've done is reflected it. So this is negative f at x, or negative sine x. Now let's apply the actual stretch. So with a vertical stretch, I'm taking, again, these key points that are not on the x-axis, I'm pulling them away. I'm stretching them away from the x-axis. So this point here used to be 1 unit away from the x-axis, but I want to quadruple it. So instead of being 1 unit away, I'm going to be 1 times 4, which is 4 units away. So this point, that's a minimum, is going to get pulled all the way down to -4. And then this point here, that is a maximum right now, its distance from the x-axis is 1. So I want to quadruple that distance. And again, it will be 4 units away, but this time in the positive direction. Okay, so really all you're doing is taking the y coordinate, so the -1 and the 1 on those points, and multiplying them by 4. With your vertical transformations, whether it's the stretch compression or the shifting up, down, it always affects your y coordinate. Okay, so now here is our final transformed function. So I'm going to label it g of x. You can also label it -4 f at x if that makes you happier, or -4 sine x, whatever you want. You have options here. So now let's go ahead and do our domain and range. Because this is sinusoidal and we know it goes on forever in that wave pattern, the domain is just x is an element of all real numbers. But our range now, because I pulled those max and mins further apart, my range is different. It is now y is an element of all real numbers, but y is greater than or equal to -4, or less than and equal to +4. And there we are. That is our sine function that has been transformed. Let's try a square root function. So, of course, we'll start off by plotting the key points of the square root function. So remember, this looks like half a parabola, but inverted. So we have 0, 0, 1, 1, 4, 2, and 9, 3. Because those are the nice perfect squares. And I am, of course, going to label it. Okay, now let's write the transform function. So why don't you pause the video here, write down the transform function and the transformations that you are applying, and then come back to the video. All right, so we have a reflection over the x-axis and a vertical compression by a factor of 1/2. So that means these points here, not only are they going to get reflected so that they're facing this way, but they also have to get closer to the x-axis because we're going to squish all of them in. So in this example, I'm going to do it all in one step. So because your vertical stretch, compression, reflection affects the y coordinate, I can just take the y coordinates of these key points and multiply them by -1/2. And when I do that, I'm reflecting and compressing at the same time. So the point that's at the origin, that's not going anywhere. But the point that is at 1, 1, if I multiply this 1 by -1/2, I'm going to get -1/2. So that's the new point. So that shows that if this were reflected, it would go down to -1, but then I squish it in to -1/2. Let's try the next one. The point at 4 has a y coordinate of 2. If I multiply 2 by -1/2, I get -1. And again, visually, I would take this coordinate, reflect it so that it goes to -2, and then squish the distance halfway. The distance right now is 2 units away from the x-axis. Half of that is 1, and there it is. And now finally, at 9, the y-coordinate is 3. 3 times -1/2 is -1.5. And there we are. We have reflected and compressed all at the same time. And I'm going to label that g of x. And it's your choice here if you want to do it in 2 steps like we did in the first example, or in 1. Okay, let's state that domain and range. X is an element of all real numbers, but x has to be greater than or equal to 0. So that's the same as the base function. But for your range, because we reflected, now y has to be less than or equal to 0 because everything is below that x-axis. All right. So for this C example with the parabola and the transformation 1/4 f at x, I want you to pause the video and do the whole example. Write the equation, write the transformations, and do all the graphing. And then come back to check your work. All right, so for the actual function, we should have 1/4 x squared, which means we are vertically compressing by a factor of 1/4. So we are hoping that this parabola will be squished and closer to the x-axis. So here is my original parabola, and I have taken all of these key points and I've squished them in. So the point that was at 1, both of them here, when I multiply it by 1/4, they should be 1/4 of the way. These 2 points here that are 4, they should now be at 1 because I squished them down by a quarter. These points at 9 should be at approximately 2.25 to get this compressed parabola. And now if you look at your domain and range, hopefully you have x is an element of all real numbers and y is an element of all real numbers, but y is greater than or equal to 0. All right, let's do our final function, and we have the rational one. So again, I want you to pause the video and try it on your own. Remember, when you draw your base function, you have those 3 key points to the right of the y-axis and to the left, and it might be a good idea to draw in those asymptotes so you have something to guide you when you connect the dots. So try it out and then come back to check your work. All right, so hopefully you have 3 times 1 over x for your equation, which means you have a vertical stretch by a factor of 3. Now here is our base rational equation with those key points. I'm going to take all of them and triple their distance from the x-axis. So the point that is at 0.5 comma 2, that 2, when I triple it, will now go to 6. Notice the x-coordinate isn't changing. It's still at 0.5. It's just the y is tripling. The point that's at 1, 1 will now be at 1, 3. The points at 2 comma a half will now be at 2 comma 1.5. And then you can connect. And just try to follow the curve and your asymptotes. Okay, and then we'll do the same thing on the left. So the point that's at negative 0.5 will now be at negative 1.5, negative 3, and negative 6. And then again, follow your asymptotes, which I didn't draw in, but it is on the x-axis and the y-axis. And your asymptotes aren't moving with a vertical stretch or compression or reflection, that they only move with the shifting. So now we can go ahead and state our domain and range. Oh, and label g of x. So for the domain and range, it is the same as the original rational. So x cannot equal 0 because of the asymptote. And for your range, y cannot equal 0 as well. And there you go. Those are your vertical stretches, compressions, and reflections. Make sure you know how to communicate it properly. And you're just starting with that base function and then applying the a value to the y coordinates. I want you to remember vertical transformations affect the y's. So when you moved up, down, it was the y's that were being affected. Same thing, a vertical stretch or compression or reflection, we were applying that factor to the y coordinate.